Please, Enrique.
Okay, thank you very much for attending this talk. So I will be talking about the formation of pair instability mass gap binary black holes. And to do this, the model I will talk about needs hypercritical accretion during a common envelope in a massive triple system. So thank you very much to the organizers for allowing me to give this talk. And I would also like to thank my collaborators, Alejandro Viña Gomez, Fabio De Colle, and Diego Lopez Cámara, which are also attending this CEPO meeting. So let me go to the next slide. So first of all, what's the pair instability mass gap? Basically, if we have very massive stars above 140 solar masses, they will develop a very, very massive core of carbon and oxygen, which will burn really, really hot. So hot that the photons which are produced there are so energetic that they may produce electron-positron pairs. And when this happens, the pressure from the radiation pressure of the photons drops, and this carbon-oxygen cores collapse. They heat up as they collapse, and they turn on a runaway thermonuclear process that disrupts the whole star, and there's basically no compact object left behind. So this happens for stars which are above 140 solar masses. If you start with a star which is slightly below this limit, it should be somewhere around 140, 130 for the most plain vanilla models, then this runaway process is a little bit different, because as the carbon oxygen core collapses, the pressure rises, more photons are produced, this stops the collapse, and you get these pulsations which shed a lot of material, and you can end up with a final product, a black hole, which is around 50 solar masses or so, as you can see on the plot on the right-hand side from some models from Farmer et al. Now, there's lots of, when you talk about massive stars, there's lots of uncertainties with the models. So we actually don't know exactly if this plot is perfectly correct, but these are some of the well-accepted models. But you could still play with the carbon-oxygen burning rates and other ingredients which may shift this maximum, predict that black hole mass from this pulsational pair instability supernova. So the idea is below 140 solar masses, you can get this pulsational pair instabilities, which will give you black holes up to 50 or 40 to 50 solar masses. Then you have a gap to 140, and stars which are more massive than that will probably, rather than explode thermonuclear from the carbon oxygen burning, will collapse directly into a very massive black hole. So there's this gap between 50 and 140, but this gap may move a little bit up and down depending on the ingredients you put on these massive stars. Then the next thing that happens is, so you have this prediction of a gap. However, with black holes, as I mentioned, there's always these issues. People would not believe that NGC 300X1 or IC10X1 had black holes with 20 solar masses. Basically, all the models were saying, well, 15 solar masses should be the limit, so we're not sure your measurements are correct. And then came, for example, the first detection of a gravitational wave, 150914, which found 230-something solar masses colliding with each other, and then they say, okay, so there can be more massive black holes. Then there's this pair instability supernova mass gap, and then we find 190521, which has two black holes right in the middle of the pair instability mass gap. One with around 86, the other one with 65 solar masses, which merge, they form a 142 solar mass black hole in the end. So basically what I'm going to try is to show you a model where we can produce this out of 50 solar or less, or actually 45 and 40 solar masses for the particular model I'll be showing. And we can grow them to be in the pair instability mass gap with this model and produce this kind of a system. The other thing is that our model also allows us to explain a wide variety of spins, which are shown on the right-hand column of this slide. So this model is, in that sense, very versatile. So what are the main ingredients? So first, let me put a little bit of controversy here. So I want to talk about hypercritical accretion onto black holes. And one thing that you can notice in the literature is that whenever people are talking about accretion onto black holes, they will say, well, we know that the mass cannot be larger than so much because we observe this luminosity, and the Eddington rate tells us that, that a black hole cannot accrete above that. Well, if you are talking about Bondi accretion, which is spherically symmetric, then that limit could work. However, when we are accreting mass into a black hole, usually it's by Rochelov overflow or probably a common envelope or Wien-Rochelov overflow. And accretion is definitely not Bondi. You have very different symmetry. Plus, the other thing is black holes, neutron stars, are very tiny objects compared to their accretion disks. So definitely you will have lots of angular momentum, which will not allow for Bondi accretion. It will not be spherically symmetric. So it's usually not apt for modeling these things. So if we were to limit to Eddington, then these systems that I will be talking about would definitely not form, because you would need tens to hundreds of millions of years to form. However, what we have when we have Rochelov overflow is Bondi accretion, which is cylindrical symmetric, which means you can have an Eddington limit free equatorial inflow, and the radiation can go through polar outflows. So in this case, when you have this geometry, you can have super Eddington accretion, which usually goes from Eddington limit to somewhere around 10,000 to 1,000 times super Eddington. Usually a value that's taken there is around 3,000 times Eddington. There's one more thing that can happen. If the accretion rate goes above what would give you 3,000 times Eddington, you can also have hypercritical accretion, which is above what I'm calling C, or super Eddington accretion. In that case, the material can become opaque to photons. You trap them, you advect them, the material heats up to high densities and to high temperatures, and also large densities. And then the neutrino cooling takes place. Once neutrino cooling takes place, you could in principle go back to Bondi accretion, because now what's relevant, for example, in supernovae, where you have little angular momentum, accretion can be Bondi, but the Eddington limit that becomes relevant is that for neutrinos, which is about 16 orders of magnitude above the Eddington limit for photons. Now, let me call your attention to the formula. It looks ugly down here, but this is the accretion rate for Bondi hole, which is what we'll be dealing with. And I want to notice that you have a dependence on the mass of the accretor squared. So the accretor becomes really important. And the other thing is, in these very massive systems, the typical orbital velocities can become large, around 10 to the 7 centimeters per second. And those are usually around an order of magnitude larger than the sound speed in the medium, which is 10 to the 6. So this formula can simplify by removing the sound speed. So what we have on the right-hand side is telling us more or less what to expect for the accretion rate when we have these very massive black holes around 50 solar masses. So basically, we have 10 to the minus 5 solar masses per second, or up to there, which is about a solar mass per day. So this is what we could expect when we have Rochelov overflow or a common envelope with a 50 solar mass black hole. So we can expect either C or HCA, which are super Eddington, or more likely hypercritical accretion in these systems. We have been doing experiments in wind tunnels with the mescal code by Fabio De Colle, and we indeed find these accretion rates. These are actually for smaller objects. So the first plot on the left, you see the mass accretion rate in solar masses per second. This was on our first paper. We had the wind tunnel and we were launching jets to see whether the jets would interfere with the accretion rate. And what we find is they usually don't make much of a dent. We have something between 5, if we have low resolution, you can see that we can even reach Bondi-Hoyle-Littleton. But once we increase resolution in our simulations, we settle somewhere a few times lower than the Bondi-Hoyle-Littleton accretion rate. The plot right below that, now the accretion rate is in grams per second, but it's basically the same order of magnitude. In this one, what we did is we put jets which are self-regulated. So depending on the accretion rate we get, we have a different luminosity. The accretion rate drops, then the luminosity drops, which allows more accretion. Then the jet luminosity goes up, and they eventually settle depending on the parameters we choose, but it's around the same order of magnitude as the first paper. For the third paper, we decided, well, we have this wind tunnel. However, this should be
2 minutes.
Thank you, in a simulation where we have much more things going on. So we added Coriolis and so on to try to emulate what's going on in the star. The other interesting result is we seem to be getting flows which are already starting to form accretion disks at 10 to the 11 centimeters, which is our inner boundary. So it is likely that we could launch jets from those disks. So the second ingredient is when we have very massive stars. Mo and Di Stefano have shown that it is more likely to have triple and quadruple systems. So the range where we are investigating, this is likely to happen. We borrowed a very nice result from Comfort and Insart from the last couple of years, where they find that even if they put a binary in a common envelope, the accretion rates, regardless of the inclination, do not drop more than a factor of 1 or 2. In the case where the binary is very separated or where it's very close. The intermediate case may have a little bit of trouble if you include the wake of one of the black holes interfering with the other one, but the results are still not dramatically different apparently. The third ingredient I take from Shashreen Mohammed, who's also in the audience here. They basically model, so around 2007, we were discussing, not with Shashreen, but when I was doing my PhD, how to form these central engines for gamma ray bursts out of binaries, and how some of the measurements of spins in black holes were conflicting with some of the evidence. So Cygnus X1, you needed a directed wind to explain some of the properties there. And at that time also came Mohammed's result, where they basically simulate a directed wind when the star is very close to filling its Rojkov. It can focus the wind and transfer very efficiently mass. Later, Elmela did this for precisely these high mass X-ray binaries, and they find mass transfer rates which are not conservative, but they are, if I remember correctly from talking to Shashreen, she could get up to 70% in the efficiency of the mass transfer. What Elmela finds in their simulations is up to around 20%. So the secret recipe for our model, so we have to mix these 3 ingredients gently. So we have here some model. We start with 120 solar mass and an 80 solar mass companion in the inner binary of our triple system. We let them evolve for about 3.5 years. You can see on the right-hand side that at that point, the primary fills its Rojkov, transfers on the left-hand side panel about 30 solar masses to the companion, bringing in 210 solar masses, and about 40 to 50 solar masses can be lost from the binary during this common envelope. The secondary you can see on the right-hand side that gets recycled, so its lifetime gets extended a little bit, but eventually at 4.5 more or less years, it fills also its Rojkov. And from the left panel, you can see that it loses another 70 or so solar mass. If this happens in a system where you have a third star, a little bit less massive than the secondary, and the outflow from the common envelopes or the other mass loss is the escape velocity or slightly below the escape velocity for the secondary, you can see that, as for example, Kashi and Soker in 2012 mentioned, you could have fallback from a circumbinary disk, but anyhow, the escape velocity is for the binary, not for the tertiary system. So if the velocity of this mass is comparable to the orbital velocity of the tertiary, then you have something similar to what happens in wind-Rochlov overflow. And you could capture several tens of solar masses in the tertiary star. You don't care if you capture 80 solar masses and it goes above the per instability supernova gas, because this star will eventually expand before going into this stage when it starts burning helium. And it was also recycled by this accretion, so it will also take a delay in time. And then this third star works basically as a reservoir of hydrogen, which you can later bring back in a common envelope to the binary. What this
you need to close soon.
Okay, just need 1 minute. So
okay.
What we have is plotted is the mass of the secondary. We left at 40 solar masses, and the primary at 45, which is basically taking the numbers from Comfort and ISARC, so that they will accrete the 65 solar masses necessary to reach 86 and 65. And this can be done in about 10 days at the accretion rate from 1 decoileton. There are several other sources which could benefit from systems from this kind of a model. I leave here a chart with some of the gravitational waves which have a component, at least in the per instability supernova mascot. There's also a binary in the LMC which has very, very massive Wolf-Rayet, which could in principle go through something similar to this. So conclusions, we need hypercritical accretion to explain these systems. A third massive star could produce this mass transfer mode, this common envelope Rochlov overflow, which I have called, and work as a reservoir of this hydrogen. There are several candidates in the gravitational sources that could benefit from this. One in the LMC at higher metallicities, and the orbital inclination between the binary and the tertiary with this much mass accretion rate can explain for a wide variety of spins and different inclinations, which can also explain the observations. Thank you very much.
Okay, thank you. Please, questions, comments. Stefan has problems with his Wi-Fi.
I'm back.
Good. Take it. I think I thought you're sending me a regular mail and went to the post office.
That was a terribly embarrassing 20 minutes. I'm so sorry, Enrique.
Okay, so.
Okay.
In the meantime, I finished, Stephen. I don't know if there are.
I would love a private audience at some point. I'm very, very sorry. Have there been questions?
None yet.
Okay. I see a handful.
Probably shock the audience with these very massive stars.
Paul, I know, is wise and loves massive stars and has a hand raised.
I don't know about wisdom, but the massive stars bit is definitely true. And just this very interesting mechanism. I'm wondering, so, you know, as we see more and more events with spins, you know, is this evidence of spins in these mergers that suggest a dynamical origin, that sort of hurts the case for an isolated binary or isolated system origin. I'm wondering if you found a way to make an isolated system compatible with the spin measurements. What's you know, is there going to be a way that that we can distinguish based on the spin?
Yes. So, well, first of all, if I understand correctly, you cannot explain more than about a quarter to a third of the systems we see with LIGO, with other than binaries or isolated systems through exchanges, right? But on the other hand, if you notice this mechanism, you're basically doubling the mass of the black hole. So if you double the mass of the black hole, depending on where the accretion occurs in the marginally stable or in the marginally bound orbit of the black hole, you need between doubling the mass of the black hole to 1.5 times, 2.5, to produce to go from a Schwarzschild black hole to a full Kerr black hole. So from 0 to 1. If you have an inclination, let's assume that you had tidal synchronization and whatnot in the binary, but however, the binary does not need to be in the same plane as the tertiary. So if you account for those effects, then you can explain a wide variety of spin from 0 to 1, so the magnitude of the spin, but also the inclinations of the spin. On top of that, you have the collapse, which will lose some of the mass, and will give you some kicks, even only black burst or a little bit of supernova, 10% to 40% mass that you expect to lose from releasing the binary energy, the binding energy during collapse. So those things can also give you some kicks, which can still further alter whatever spins you got from the binary interaction with the common envelope of the tertiary. So there's a lot of mechanisms that can allow you to explain not only the magnitude, but also the issue if particular a triple system. Now, binary is probably a bit more complicated, but this system, as I mentioned from Mo and Stefano, would preferentially come from triple system, and even 4 stars at that star could do in this case. So yes,
thank you, Enrique. I think that's one of the first times I've heard someone say that the binary would be more complicated than the triple, which is nice. On which note, I think Sylvia has a question.
Thanks. I'm still laughing about that remark, Stephen. I have to say, Enrique, thank you for the talk. I really found it very interesting. And I have 2 questions for you. So this wind-workshop overflow, or at least the way that Shazrena described it in the past, happens under very specific conditions. And I was wondering if you thought about if those also are valid for massive stars. I'm thinking timescales, wind mass loss rates. And my other question is, the work from Marta Saladino showed that systems that are undergoing something like wind-workshop overflow typically have a lot of angular momentum loss, and so the orbit shrinks, which then would probably lead to a proper common envelope phase, right? So you start with wind-workshop overflow kind of as a precursor of a common envelope phase, which might be something else that we want to discuss this week. But how would that fit in with your evolutionary channel? Right.
So over here, we have tried to put the most plain vanilla system so that it would be the most feasible. But you're right, you could have a wide variety of parameters for example, in the inner binary. So you could in principle begin the first common envelope with a wind-workshop overflow, and that would affect the end result. However, as I mentioned, we're just trying to go the most simple. So we just have a common envelope phase where you lose this large amount of the primary star, some part into the companion, and then the rest of that material is lost. It's lost in a common envelope. And as I was mentioning, the velocity of that material, of course, there's all these ingredients that we don't know from common envelopes. But if we assume that they are escape or around escape velocity from the binary, then that means they may still be bound to the tertiary. So if you have lots of fallback, and that fallback has a slow velocity compared to the orbital velocity of the tertiary, you could capture a substantial amount. On top of that, if that material falls into a circumbinary disk, it could eventually be also accreted either back into the binary or as a tertiary sweeps. If its Bondi-Hall-Littleton radius is large, which should be, then you could also capture part of that material. So we are assuming certain conditions which involve slow velocities for this common envelope outflow from the binary, which allows the tertiary to capture first in the common envelope and then in the second mass loss period, which is when the secondary expands. So there can be, of course, we have not modeled this. Even COMPAS, which is where we run these models, does not, from what I understand, does not have the capacity yet to do triples. So lots of this is mostly analytical and considering certain assumptions. But you're right. There's several ways to fill these Roche laws. In particular, we have a complicated structure with a tertiary, because one of the Roche laws, the one from the binary, is varying with time. And that can affect also the mass transfer rates with this orbital modulation and whatnot. Okay.
I think maybe one brief question from Hagai, and then we should move on. So Melvin, can you start putting your slides up? If Enrique, can you take your slides down? And
sure.
Well, and then Hagai asked his question.
So I'm just wondering about this accretion and what are the conditions that you actually have for a very efficient.
I'm sorry, I can.
Sorry?
Hagai, can you speak up a little? Or?
Yeah, so I was wondering about this hyperaccretion and the conditions that are required for this, because it sounds to me that there are many systems that might actually accommodate such conditions, and you should have, even in our galaxy, many very massive black holes just in binaries. You could just have wind overflow mass transfer, and then you should have growing black holes just by that, and we don't see them. At least we don't have evidence for those massive black holes.
Well, we don't know if we see that. If you're in the range of hypercritical accretion, then you are producing a lot of neutrinos, and these common envelopes or Roche law overflows or whatnot, which may be at hypercritical accretion, you may only see them as super Eddington or somewhere around there, because the rest of the energy is going away in neutrinos, and common envelopes, Roche law overflows, etc., are completely transparent to them. So that's kind of like an energy drain, which you cannot
this I understand, of course. I was talking about the remnants, not during the accretion. The remnants, you should have very massive black holes just lurking all around the galaxy. Well,
you are right in the sense that I forgot to mention that these models are done at very, very low metallicities. We don't necessarily expect to see these 50 solar mass black holes at our typical local metallicities. The one exception, which I mentioned here, is MK134, but it's not a very common system, right? We have this 140 solar mass Wolf-Rayet with 127 solar mass, and they may lead to something like that if the mass loss rate through winds and whatever interactions they may or may not have in the future. They are, I think, the aphelion must be 9.9 AU. So if they can manage to get a little bit closer, they could have common envelopes or whatnot. But other than that, depending on the mass loss rate from the winds of this Wolf-Rayet, they could live to these massive black holes. But if the mass loss rates are what we usually take in our models, they may end up easily in the 30 solar mass range. So
it sounds like a discussion that should go to Slack, I think. It sounds interesting. It's recorded for the future.
Thank you.
Okay, brilliant. Thank you, Melvin. And thank you, Enrique, and I'm really sorry. Okay, so we have hello, Melvin Moreno from Heidelberg, who's going to tell us about his simulations.
Okay, can you hear me and see me? And
I can hear you and see you beautifully, and if I disappear, I'm sure someone else will take over.
Okay, thank you. Okay, so I'm Melvin Moreno, and I'm a former master student of Friedrich Röpke, which talked yesterday, and I did this research that I'm going to show in HITS, and other names that other people that collaborated with me are Fabian Schneider, Sebastian Ullmann, and Rüdiger Blackmore. And okay, so we're all interested in common envelope here, and the context of the common envelope that I'm interested in is black hole neutron star systems and double neutron star systems. So we go now way less massive than the previous talk. So what I'm interested in is in these formation scenarios where you actually, in the end, have a black hole neutron star system which can or cannot merge depending on the orbital distance through gravitational waves. The very critical formation uncertainty, or one of the most critical is the common envelope, as you all are familiar with. And I'm going to study these two systems. So to do that, what I'm going to do is a 3D hydrodynamical simulation in AREPO. And the way that we set it up has 4 steps. First, we create a one-dimensional model using MESA. We choose a 0H main sequence of 10 solar masses because this will lead to a neutron star progenitor. And we will have this neutron star progenitor as our primary, and then we will have a black hole companion or a neutron star companion for the binary systems. So we take this neutron star progenitor, we evolve it until it is a red supergiant, and we reach a model which has 9.6 solar masses and 396 solar radii. Then we take this 1D model and we map it to 3D. We take, as many other people mentioned in the conference, we take the core and we change the gas with a point particle. And this allows us to reach higher timescales of simulation. We preserve the convective envelope in this process. So the convective envelope is out of the 10 solar radii mark, and we conserve that. And then we put a huge resolution into the, or a very high resolution into the envelope of 6 million cells. Then once we have this constructed, even if we have a high resolution, you have instabilities, or maybe not instability is the word, but we have spurious velocities that make the model differ from hydrostatic equilibrium, which come from, okay, I have a message here that says participants can now see your screen. Was it working the whole time?
I think that message was quite slow. We could see it all the time. Yes.
Okay.
At least
perfect,
I could.
thank you.
Yes.
Where was I? Okay. So even if we map with a high resolution, you still have some deviations from hydrostatic equilibrium when you go from 1D to 3D. And then we have to perform a relaxation to truly reach hydrostatic equilibrium and know that our results come from only the dynamical interaction between the stars. So to do that, we put the star isolated in a box for 5 dynamical timescales, and we reduce the velocities artificially. And after this, we let it evolve freely for 5 dynamical timescales. And this allows us to check with enough time that the star will just remain in place and be completely stable. After we do this, we have a very stable 3D star, which you can see on the right. I am just showing here a density profile of the MESA model, which is the gray line. And then you see the rest of the lines is how the 3D model evolves over time. And I'm not going to go into detail, but you just can see that the profile really matches very well with the MESA profile, except outside of the star where you have a pseudo vacuum. So this is not important. And in the very inside where we replace material, which is not important as well. And now we take this star and we create 2 binary systems, one with a 5 solar mass companion, which is a typical black hole mass, and another different one with a 1.4 solar mass companion, which is a typical neutron star mass. And these are point particles. They are only interact gravitationally with the material. So first, we take this 5 solar mass companion, which is the black hole, and I'm going to show a video which hopefully will work. And so, as I said, we just take this star in 3D, and then we place the companion here. You see the plus in the center is the core of the giant, and the cross is the black hole. And if we let this evolve over time, of course, the black hole spirals in, and you have a plunging, the orbit decreases. You have a very beautiful spiral shape in the envelope. And you see how it gets diluted over time. The density decreases because the material is being expelled. So numerically, what we're seeing here, if you look at this figure on the left, the blue solid line is the orbital distance. And of course, you have a huge plunging, and then you have a more or less stable orbit, which we reach there, which is decreasing very, very slowly and even increasingly slowly over time. You have some bumps, which actually represent the eccentricity. And then the dashed lines represent how the mass is unbound, or the fraction of the unbound mass. So this is how much mass is unbound. According to different criteria, divided by the mass of the envelope. And the criteria that we use for the unbound mass are, I think also Ursula already talked about these criteria, and other people also use them, is only kinetic energy, kinetic and thermal energy, and also including recombination and or in general internal energy. So of course the expelled material increases over time, and these are the final numbers. So with the internal criterion taken into account, we have 98% ejection of the material by the time we stop the simulation. And in the thermal and kinetic, we have roughly 50% of the material, which is still increasing. And we expect it to just be increasing until it reaches the internal value once the recombination energy is kicking in. I think this has already been discussed. If not, please ask me in the questions. We reach a final orbit in this simulation of 46 solar radii, which is pretty wide. This corresponds to orbital period of 11 days and an eccentricity of 0.065. And this is only the final eccentricity. Of course, at the beginning is way bigger, but this is what we have in the end. Very similarly, we do for the neutron star. So again, I just placed the neutron star above. You can check here. I just placed the neutron star above, which is 1.4 solar masses, and the it proceeds similarly. It spirals in very deeply, but then you can see first that it's way deeper than in the other one. This is because of the mass ratio, and also you see that it's not really spiraled at all. This is a very striking difference with the previous one. You really have here a very unstructured flow, I would say unordered, and you don't retain the spiral shape that you had with the black hole. And the reason for that, I have my own ideas, but I don't think it's so easy to pin down to one specific reason. But it's a very striking visual difference that you can see there. Interesting. Okay, and then numerically, the figure is identical. You just can see by roughly that it goes deeper and that the oscillations are way smaller because the eccentricity is a bit smaller, and also because of the orbit is smaller. So numerically, we have 99% ejection with the internal criterion, 70% roughly with the thermal criterion, 54% of the mass ejected with the kinetic criterion, final orbit 15 solar radii, orbital period 3.2 days, and the eccentricity is 0.045. And finally, another interesting thing that we found in these simulations are these magnetically driven outflows with 3D Röpke talked about yesterday. I have not looked into much detail into these features, but I can say that they are very different in shape, of course. On the left, you see the black hole, the jet, oh, sorry, maybe not jets, but outflows, as I should say. So these outflows are way developed, very beautifully shaped on the black hole case. But on the neutron star case, you rather see only on one side, not so big, not so structured. So again, resulting from the maybe not so ordered shape of the interaction. So here I just have again the conclusion slide. I quote again my final orbit and my ejected mass that I expect in these two systems, and then taking this final radii, what can we think? What can we say about the future evolution of the system? So both systems will have a stable mass transfer phase. In the case of the black hole, because of the mass ratio, the orbit will actually expand even further than 45 solar radii. So you will have a black hole neutron star binary system if the system survives the kicks, the supernova kick and so on. But this brings it to a distance that is very wide to actually reach a gravitational wave, so a merger through gravitational wave radiation. And then in the neutron star case, you also expect this stable mass transfer. In this case, the orbit will shrink, but only 30% or so, according to our estimations, which is in principle not enough to reach the range where these two neutron stars would merge. So you will have after the supernova kick, if the system survives, you have two neutron stars orbiting each other. But so far that in principle, we don't expect them to merge through gravitational waves. And that's it from my side.
Thank you, Melvin. It was lovely. So I think Haggai's hand was from the previous talk, in which case, Sylvia, please ask your question.
Hey, Melvin, thanks for another very interesting talk. I have a question, but if I miss something, then just correct me. So what I remember from previous work, for example, from Ursula de Marco's paper, is that with a lower mass companion, you would shrink less. And you seem to find the opposite.
No, in principle, if you think for the same mass of envelope, if you have the same envelope, if you have a less massive companion, you need to spiral in deeper to give the same orbital energy to eject the same amount of material. So in principle, you would expect, of course, there are more complicated things into play than that, but in principle, you expect that lower masses actually cannot eject the material successfully or have more problems ejecting the material, and then they orbit deeper because they have to release more orbital energy.
Yeah, I don't know if Ursula is maybe around. If, as far as I remember, she gets, or in that paper at least, is presenting an alpha dependence. Well, that alpha depends on the mass ratio, like in the opposite way of this. It makes absolute sense what you're saying, but
no, for sure. And actually, I want to point out one thing, which is interesting. So, of course, very roughly, as you say, this balance you cannot do one-to-one comparison because the whole dynamics of the system will change. And actually, if I can show something here very quickly, you can see that the final, let's say, like the stable orbit in the neutron star mass companion, so in the neutron star system, is reached, let's say, faster in comparison to the black hole. Of course, this is difficult to compare, but the star spirals in faster and also ejects the material faster. So if you try to compare, this is not easy to do here because the numbers are not exactly the same, but if you try to compare how fast the neutron star ejects the material compared to the black hole, actually it does it earlier. So I think this, depending on how you analyze this, they could give the impression that the alpha are different throughout the simulation. Anyway, what I'm trying to say is that even though what I find is that this one spirals deeper, I think the dynamics change a lot and you have non-intuitive things happening, like the less massive one ejecting more material faster. So it's complicated anyway.
Thank you. Thanks for explaining.
Morgan, just in time. Morgan, please.
Yeah, thanks, Melvin. This is really fun to see. I wondered if you could talk a little bit more about how you end up with the flow that you were calling disordered in the neutron star case. And it looks to me like something that we're seeing is kind of like Rayleigh-Taylor instabilities where there's denser fluid on top of lower density material, and some of those plumes are then falling back toward the center. And I was wondering if you could talk a little bit about how that comes to be.
So I can maybe show the video again. Okay, I honestly I honestly cannot like answer your question fully because I don't really understand how this instability comes into play here. So I mean, I just have to say I cannot answer your question. I would only assume that my initial very rough guess from my master thesis is that the black hole has way more mass and it has a wider orbit, and then it imprints it imprints this let's say like what's the name for that, anyway, like it imprints the orbits on the envelope as it's passing around. But this star, the neutron star, goes very deep and it has very low mass, and then this influence is not so big and it's lost to other instabilities or other factors that are also happening in the flow. This is just like my rough estimate, but as I said, you probably have better
And the
idea
assumption
of
that Fritz isn't about to ask you a question, I suspect he has an additional part of that
yeah,
answer.
probably, yes.
Yes, indeed. I just wanted to comment on this. So I think, Morgan, you're correct. So this is kind of a buoyancy instability. Sebastian actually has looked into this in his first paper, and you can actually sort of check the sort of equivalent instability criterion. You see that inside these spiral shocks, you get this instability. And the question is only how strong it develops and whether this really interferes with the flow much, and why this actually happens in this case more, in the other case less. That's something we have to look into, but we're not surprised to see these.
I think Melvin's point just now about the sort of relative strength of the spiral shock pattern and like the growth rate of these modes is really kind of interesting to think about more. But this is beautiful. Yeah, thanks for sharing.
Okay, I think Haggai's hand was first, although perhaps Paul was going to address this exact point.
I am, but I could wait for Haggai.
So I was wondering about the accretion during the simulation. I think I asked Fritz about it, so I'm not sure. And at that time, when I asked him, he did not have an answer. How much accretion should we have on this compact object during the inspel?
So I just want to first clarify that this we don't have any.
I can't hear you.
Can you hear me? Hello?
I can hear you, and Haggai is now louder than he used to be, but it sounds like he can't hear you.
So you can hear me?
I can hear you perfectly well, yes.
Okay, yes. So I don't know if he can hear me. I just want to clarify that here, as I said, we model the black hole and the neutron star only by a particle, so we don't have any kind of simulation accretion. Another question is what is expected, and I think from what I read in the so I can only quote, of course this is from my master thesis, but I can only quote Tauris. He was studying the formation of double neutron star systems, and he said that the neutron star will not change much the mass throughout the whole interaction, the first common envelope, the mass transfer, and so on. And I think he was saying numbers of, in the paper, he and others was saying numbers of only maybe like 0.2 solar masses at most. I think this is the order of magnitude. In any case, even if I don't know the exact numbers, just have in mind that this envelope that I'm showing here, just the envelope is 7 solar masses, and the amount of mass that the neutron star could accrete would be very small. In the case of the black hole, I don't know. I cannot answer, but I suspect that it would be very similar.
Thank you. And I think Paul wanted to contribute to the discussion about the shape of the flows.
Mm-hmm.
Yeah, I wanted to ask about angular momentum, actually. It seems like they're probably both giving comparable amounts of angular momentum to the gas, and yet you don't get the strong shocks, spiral shocks in the neutron star case. So I wonder if you've looked at the the distribution of angular momentum in the envelope. I'm not sure exactly what's causing this, but it's really interesting. And thanks for a great talk.
Thank you. No, I'm not sure I understand what you mean the distribution of the angular momentum. So you mean like how the angular momentum is being transported inside the system?
Yeah.
Like in the envelope?
Yeah,
No, I mean,
that's right.
we didn't look into this, but it is, of course, very interesting. I think, no.
Okay.
No, I mean, I cannot answer, but yeah, that's a good point.
I think there's a lot more interesting discussion to go on in Slack. Sylvia, I've been assuming that your hand is still up from the previous question, but if I'm wrong, I'm sorry. I don't know. I'm also interested for the Slack about whether your 6 million cells should be a minimum for calculations I trust, but I think that's another conversation to have offline. I don't know whether Noam wants to say something, but maybe we could save it for the discussion.
Okay, your call.
Okay, go on, Noam. I can't say no to you. Quickly.
No, I just want to, Melvin, very nice talk, but when you say a little bit mass, you need to compare it something. Let me be clear. What mass did you say the neutron star accretes? Is
I'm quoting from. Yes, I'm quoting from my head that.
Yeah, this
number.
is this is a huge amount of mass. I assume it can be correct because about 10% of this you launch in jets, and if it's an escape velocity, the amount of energy you can get here, it's actually like a supernova just from the jet. So when you say it's not about the physics, but what you say, a little bit mass is compared to what? If you compare to energy of supernova, you have it just from the accretion and energy of supernova, say 10% in the jet. The other is cooling. The previous talk, it talked about it, cooling by neutrino. But 10%, even if you take 5% of this mass, you can get 10 to the 50, 10 to the 51 air. So you have a supernova.
I think the point is clear, and I think we should probably move on. I'm assuming that people are willing to skip the 10-minute break in favor of finishing more quickly. If anybody objects, say now. But in that case, can Anders please bring his slides up?
Yes, just a moment.
Okay, so we're going to a different type of transient from the ones in the previous session. And
yes,
very exciting.
So it's time for a supernova talk. Actually, this talk is very well placed after the previous one, because what I will try to convince you about is that this particular supernova I will talk about, 2006 GY, is something quite similar to what we just saw, except that instead of having a black hole or a neutron star that goes into a companion envelope, the model scenario that has emerged here for this supernova would be to have a white dwarf instead that is spiraling into a relatively massive star, and then explodes as a 1A supernova, and we have an interaction with the ejected common envelope. So 2006 GY, as you know, in naming supernova, it is exploded on 15 years ago, and in fact the data, we stopped collecting data 14 years ago. So what happened last year was that after maybe a decade of no progress at all, we had a sudden breakthrough in understanding data has been lying around for 15 years, which doesn't happen that often. And I will show you what the story is here. So 2006 GY, one of the brightest supernovae we have ever seen. You see the light curve here, the red dots. And you can compare that to sort of normal supernovae, which you have down here. So when it was detected in 2006, it was by far the brightest supernova that we had seen, and it remains today, I think, one of the 5 or 6 brightest supernovae ever observed. If you integrate all this luminosity here over time, you recover a radiated energy of about 10 to the 51 ergs, which is then about the factor of 100 larger than these normal guys down here. So there's been a lot of models proposed, of course, over the years here, but the general consensus that has emerged is that what we're seeing here is some sort of diffusion process where we have an interaction with the supernova and a massive CSM of some kind. And the numbers we are talking about is that you need to have something of order 10 solar mass CSM outside of the supernova. We can actually see the CSM. If you look at the spectrum down here, this is a zoom in on H alpha. So you have some fast material here. And then you have these narrow lines. And these narrow lines are emitted from the unshocked or unaccelerated CSM. And we can infer from the line profiles the expansion velocity of this gas, which is of order of about 100 kilometers per second. And furthermore, we can combine information about the emission radius and this velocity to infer that this CSM was ejected only about a century before the supernova exploded. So this is something quite, this is not something you easily do with winds or even LBV eruptions and so on. Nevertheless, most of the models that we had over the years, they have focused on massive stars. There's been two classes mainly. One is the pulsational pair instability supernovae, which we heard about in the first talk by Enrique, where you have subsequent shells ejected by very massive stars. So maybe when these shells collide with each other, can you have something like this? And the other type of models have focused more on something like Eta Carina. So a massive star that maybe has a giant eruption and then it goes core collapse, maybe a century after that. It's worthwhile to remember here, though, that when we talk about supernovae, we always have to consider both the channels. We have massive stars that make supernovae, we have white dwarfs that make supernovae. And the white dwarfs we normally call type 1a supernovae, and the other ones we call different things depending on how much mass loss the progenitor had and so on. And by a pure coincidence of nature, both of these completely different explosion processes give you kinetic energy of order 10 to the 51 ergs to the ejecta. But there are differences. The ejecta mass of the white dwarf is done of something in the order of Chandrasekhar mass, whereas the massive stars are typically larger ejecta masses, maybe by a factor of 10. And there is a second important difference which will come into play here, and that's that the amount of iron that you produce in a 1A explosion is about half a solar mass, whereas in the core collapse supernovae is about factor 10 times smaller. And this iron is not made as iron itself, it's made as 56 nickel, which then radioactively decays into iron. Sometimes we do have CSM interaction. Typically, we call these supernovae type 2N, and historically from the 60s or 70s, it was always assumed that these are massive stars that are colliding with their own winds. In 2003, we started discovering white dwarfs that are exploding and interacting with circumstellar material. And we actually only have a handful of these objects known so far in this type 2A class. So let's go back to 2006 GY. The last information we got on the supernova was this spectrum. This is the last spectrum obtained. There was 1 year after explosion. And after that, the supernova faded it was so dim that we couldn't really get any data on it any further. And here something happened which really doesn't happen often in supernova research. Some of the strongest lines that we were seeing could not be identified. And these are the lines that you see here with the blue arrows, around 8,000 angstrom. So we have never seen these supernovae, these lines in supernovae before. And the authors here in this 2009 paper, they speculated a little bit, but none of these suggestions have survived further scrutiny. So up until last year, we were stuck actually. We clearly had some kind of smoking gun signature here, and no one could figure out what we were looking at, even which element we were looking at. The only thing we knew was that the material of the supernova was expanding with about 1,500 kilometers per second from the Doppler broadening of the lines. So the important breakthrough came by finally being able to identify the lines. So we demonstrate in this paper from last year that one can very convincingly show that these lines must be due to iron 1. What you see here are the observed lines compared to predictions. If you take about half a solar mass of iron 1 and you excite it to a few thousand degrees and you put it at the distance of the supernova, and these lines emerge exactly as they should. And the first thing we set out to do was try to constrain the amount of iron in the supernova. And I'm not going to go through all the details here. It was quite a lengthy analysis, but the final result was that we could limit the mass of iron between 0.3 and 2.1 solar masses. So this is a large iron mass, and these two sort of main classes that we had before, they immediately had problems here. The first one, pulsational shell collisions. These shells don't have any iron at all. So I don't think I use too strong words when I say it's not going to work. That scenario is not, it will be, I can't see how to make that consistent with these iron lines. Core collapse supernovae are not so immediately ruled out, but there are lots of problems here. They generally don't make so much iron. And we always see oxygen lines from these kind of supernovae, which we don't see anything in the supernova. So we took the bold step to think a bit outside the box here and said, are we actually looking at the massive star? Or is this actually a 1A supernova? So as you recall from the first slide, 1A supernova makes half a solar mass of iron, and that's exactly what we need here from the new identification of these iron lines. So that's, I put here sort of three arguments that seems to work in the right direction for this scenario, that you have a white dwarf that then spirals into the envelope of a companion, it ejects a common envelope, and then somehow explodes within about a century or so. So we have the right amount of iron, and importantly, we have an explanation now. It's like, why is this happening within a century of creating this massive CSM? Like, there is no such synchronization mechanism in massive star scenarios. There's no known physical links that creates massive eruptions of that order with core collapse. And the third argument is, we set out to really dig through the common envelope literature here. And what we found was general support for that this process seems possible, or it seems consistent with current simulations, that one can have this kind of systems form, you can have an in-spiral, and you can eject more or less the whole envelope on time scales that match this. And this is also related to the talk that we just saw then. So we set out to test the idea. I will keep this short. The punchline is just that it sort of works out quite well. Here is a model spectrum where we took a 1A supernova and we just slowed it down. We said this is gonna hit a 10 solar mass CSM, so it's gonna decelerate very dramatically because you have a 1 solar mass ejecta slamming into a wall of 10 solar mass CSM here. So what's happening is that you're converting all your kinetic energy, all your 10 to the 51 erg is converted to radiation when the supernova goes into this common envelope then, which is relatively close by still. The model reproduces these neutral iron lines. This is sort of the first test that any model has to pass here, and it looks consistent. If you haven't seen supernova models before, if you're used to seeing like stellar models, this looks horrible, but trust me, supernova modeling is a different game, and when we get this kind of comparison, we are generally happy. So we would call this sort of a good model. We then said, what about the light curve? Can we make this extremely bright light curve? And so we took again a standard 1A explosion model, and we took a publicly available radiation hydrocode, and we just slammed it into a shell of material with different mass. And yeah, you can sort of make the right luminosity and duration here. Now, this modeling is quite simple, but we tried to say, okay, what is the mass of the CSM that we need? And the sort of best value we get is about 10 to 15 solar masses of the CSM, which is kind of consistent with earlier estimates.
Probably a minute or so left.
Yeah, thank you. I think I actually only have the summary, and I think I would rather leave this as my last slide, because for the purposes here of this conference and for the discussion here in this session, probably what's most fruitful is that all of you just will, for now, believe in this conclusion. And if we assume that this is the right model scenario, I hope we can have some discussion about these 3 points here, because there's a lot of things that need to happen here, right? We need to get the white dwarf to come close to a massive star, red giant or red supergiant. That seems possible from what I understand from binary population synthesis modeling. It doesn't happen that often, but it does happen. We need the white dwarf to spiral in, eject all or most of the envelope, and get close enough to the core of the other star that it can somehow accrete and explode. And related then to how can we actually get the white dwarf to explode within approximately 1 century of plunging in towards the core of another star. On this third point here, like the modeling we did, we're not really saying what is the nature of this companion star, because we're putting a CSM out there, we're giving it the mass and so on, right? So our best mass is awarded 10 solar masses, but yeah, if you want to have an AGB star here, so you have basically a double white dwarf merger. Of course, your ejected mass cannot really be 10, 15 solar masses, right? It's more maybe 6, 7, 8 solar masses. If you really want to have those kind of masses, you will need to have a red supergiant, and then you're instead talking about the white dwarf exploding by accreting helium at a very high rate than from the helium core. So I think I will stop there and yeah, take any questions.
Yes, questions. That's lovely. Go on, Alexei.
Thank you. Wonderful discovery. So question is, like, can you trade the asymmetry for the mass of the CSM? In other words, can you take an asymmetric common envelope ejection and realize the same light curve with a lower CSM mass?
So the CSM that was used here was spherical symmetric, right? This is spherical symmetric modeling we did. And so there is one issue now with, if you want to have a very asymmetric CSM, and so you need to radiate 10 to the 51 ergs. That's the observed radiated energy, and your energy budget is the kinetic energy of the 1A supernova, which is typically 1.3, 1.4, 1.5 times 10 to the 51 ergs. So that means, let's say you put your CSM in a disk, for example, you're not going to extract more than maybe 10% of that kinetic energy, because most of the ejector is going to go, is not going to hit the disk. So actually, what we could say is that if this is the correct interpretation, the CSM must be relatively spherically symmetric. Otherwise, we don't get enough energy out. So I think that is the sort of first thing to worry about.
Well, just the hope might be that you might have 1 to 3 asymmetry or something like that, and pull down the mass of the CSM to below 8 solar masses, so it's easier to realize perhaps with some company.
Yeah, I can also add to this point that in the simulation we used the Chandrasekhar mass white dwarf, and of course to some extent the CSM mass you need depends a little bit on the ejecta mass of the supernova. So if this is a sub Chandrasekhar white dwarf, then it could be that we get away with a lower mass CSM also, and then maybe these AGB stars come into play.
Thank you.
Other Stephen?
Oh, these are magnificent results.
Thank you.
Actually, right at the moment, there's a little analog that went off at the beginning of the month, RS Ophiuchi. And your spectra at the beginning look exactly like that system, except of course it's not going to do what you did, but it's got all of the basic physics. That is, we see the fluorescent lines in this that are being driven from the shock. There's also extended medium from the precursor. that's being ionized. And you might be able to get some constraint by looking at the fading of the precursor generated lines, not just the ones that are fluorescent, but the ones that are being ionized, because the lower ionization material at the beginning is going to then recombine. Okay, so the high ionization, the stuff that's high density, I think you've got a nearly spherical environment. But
I mean, this is definitely in the supernova field. People have started to do this thing in the last couple of years. They call it flash spectroscopy. I don't know if that's generic term in other fields as well.
No.
So yes, it is a method that is coming into use. Usually it requires very early spectra, right? So like for this object, for example, there were not early enough spectra to do this, but
yeah, but you might also have some dust here, right? So you might see that in a light echo.
True. Yes.
The other point is that as the material is being swept up, you're going to change the profiles. So you've probably got that already in the history. The one that comes closest to this, I'd suggest you guys go back and take a look at, is V407 Cygni, which showed very similar phenomenology. It would be a good analogy for what you're doing. I'm not saying that it's the same thing, but there's also a theoretical question that I have, if you don't mind.
Well, I just comment on this thing you said. I mean, of course, I think where we are now to take this further, this is what we need to do, right? We need to look for other objects to build. As long as we just sort of have one case, it's hard to put this whole thing on a really firm footing. But if one can show the same thing and sort of confirm predictions in other objects, that's the way to go. Yeah.
Well, the other is just a question. The white dwarf is going to be accumulating material for a period of time as it's going through the in spiral. Is it possible that you trigger a TNR at the beginning, so you get some kind of pre-processing?
So we spent a lot of, well, I think I should say, you know, those of us who were writing this paper, there's only 3 of us. None of us were really like experts on how a 1A supernova explodes or even this accretion physics. We did try to just talk to people as much as we could and make sure that there was no such showstoppers, so to say. And I have to say, I thought we got such a variety of answers that there was no real consensus that came out on what to expect here actually in this in spiral. But maybe that's something we can have for the discussion also.
Well, I thought that the way you might be able to constrain that is by the fact that you have no oxygen in this thing.
Yes.
And that if you have a CO white dwarf, you're definitely going to be producing that. So this may give you also some constraints on the amount of material that was actually blown off during the explosion, not just the iron.
Yeah.
You know, magnificent result. We've been bootstrapping off of your stuff, not the other way.
Nice to hear. I'm glad to hear.
It's a fantastic result indeed. I think, Noam, if you can be quick, otherwise
yes, I'll be quick. Some of the processes were worked out. The first question, how do you get white dwarf around red supergiant with more than 10 solar masses? We call it the reverse evolution, where the white dwarf is formed before the progenitor of the neutron star. Here there is no neutron star, but in principle, if the white dwarf would not collide with the core, it would form a neutron star. So this is a reverse evolution. You start with, say, 6 solar mass and 5, for example, and you transfer mass. You can start with 7 and 6. You transfer mass to the other one, which becomes a red supergiant, while the first one form the white dwarf as it should be because it's less than 8. So this is called white dwarf neutron star reverse evolution. How you get it spiraling? Because the envelope is massive enough, above 4 solar masses envelope, you get the white dwarf to merge with the core. And how do you get it to explode? This is a good question, but this entire evolution is called the core degenerate scenario for type 1A supernovae And we had several papers on this. So it's a very interesting object, and I think for me it's a support of the core degenerate scenario. So I think this is the direction to go, to connect it to lower mass star, maybe core degenerate at later time. This I had to be quick. So.
Thank you, Noah. May I just ask you one thing about that? The core degenerate model, which indeed you put forth already, was it 10 years ago, right? What is the shortest time you need for the thing to explode? You can't do it within a century, right? In that
we don't know. I call it MED, merger explosion delay. I think all model, this is my view, all model of type 1a supernovae need some delay in some system from the merger or the mass transfer until explosion. Stefan himself did the work on this in type 1a supernova from the single degenerate. So we need it, I think, in all models, all scenarios, 5 or 6 scenarios need some delay from merger or mass transfer, if mass transfer reaches a Chandrasekhar mass, to explosion. And this can be angular momentum loss or something else. But we need this delay, and I think this is an open question, but this brings us to the entire field of supernovae 1a. But your scenario, I think the way to go is to compare to the core degenerate scenario of type 1a.
I think we could have a whole workshop on models for this event. It's really fun.
Yes.
Can you take your slides down, and then Andre can put his slides up? Maybe I should say that there is a single degenerate model for O2IC, which is the Hamoy et al. Result you mentioned. So related to the mass transfer that Andre Peja showed in his talk earlier, where you have a stable mass transfer and then sudden late onset of the common envelope phase. But I don't think you can get anything like 10 solar masses of hydrogen in that. It's a shame. But it's fun. There's a whole bunch of stuff to do. And this is also fun. So on the first day, we were talking about timescales of common envelope as it relates to whether we even think alpha CE is a useful prescription to use. And Andre is maybe giving us a constraint that is really imaginative. It's really fun. So Andre, please
explain.
Hello.
So this work is done in collaboration with Hagai Perez and Erich Michaeli. So as we all know, common envelope is a crucial stage for formation of gravitational wave sources, such as double neutron stars, and it leads to a mass ejection. Looking at timescales for mass ejections, in the literature, we can find values ranging from hundreds of days up to 10 to the 5 years. So a problem here is what common envelope stage is really hard to probe observationally because it is a very short stage. So only a very small number of stars is at this particular stage at the moment. And also during the common envelope process, stars are embedded inside the gas cloud, so it's hard to observe. Triple stars could help. So if we have a hierarchical triple system where the inner binary will go into a common envelope stage at some point, and the third star is located at separation 10 to the 3 or ranging up to 2 multiplied to 10 to the 5 astronomical units. When this third companion could be unbound if mass loss proceeds fast, or if a large amount of mass, more than half of the total system mass, is lost during the mass loss. But on the other hand, if mass loss from the inner binary proceeds really slowly, so the outer companion has enough time to orbit around this mass losing system, when in many cases this triple stay bound. So we want to look in observational data and statistically compare outcomes of these processes. So we are interested in sub-dwarf B stars, post-common envelope binaries with white dwarfs, and cataclysmic variables. So the first stage, we just identified, we matched a catalog for all these types of binaries with Gaia second data release. we use location of these stars in the sky and their magnitudes converted into Gaia. And after we identified these post-common envelope stars, we also computed difference in parallax between parallax of this particular target and all stars in the field. As well, we computed difference in proper motion and angular separation. So in this plot, which we use just for visual comparison purposes, potential companions to our post-common envelope subdwarf B stars are located in the lower left corner because they have a small difference in proper motion, a tiny difference in parallax, and they are located very close in the sky. So how do we know what they are physically associated? Well, we can just shift all our targets at 1.4 degrees in declination or in right ascension direction and perform this procedure once again. And it's clear what this part of the diagram left lower corner becomes much emptier. So most of these objects are probably indeed physically associated with our post-common envelope binaries. So if we perform this procedure carefully, we can find 68 ultrawide companions to SDB stars, which translates to probability of 1.4% approximately to find ultrawide companion to SDB star. For post-common envelope binaries with a wide dwarf, we get a probability of 3.7%, and for CVs 2.5%. But the most reliable our result here is for SDB stars because uncertainty is small due to the huge number of SDB stars in our cutoff. What do we have here for comparison? We can look at main sequence stars and perform exactly the same procedure for exactly the same cuts in parallaxes. And in this case, we find ultra-wide companions in 5% of the cases, or if we add additional restrictions on properties of this companion, we might even get larger values around 9% or 7% of the cases. If you're thinking about post-common envelope binaries with a wide dwarf, a natural system for comparison could be a main sequence wide dwarf binary which did not interact. In this case, we still can find the ultra-wide companion, and we find this ultra-wide companion 4.2% of the cases. So this comparison is justified because at the different levels of hierarchy, we have a similar probability. So it means if we have what we believe is a single star, it has the same probability to have ultra-wide companion as what we believe as a binary star to have a third companion. So that's why we can compare, in principle, main sequence plus distant companion with subdwarf binary with a distant companion. So here I put the Hertzsprung-Russell diagram for companions to SDB stars. As you can see, most of them are located at main sequence, except some cloud of points below the main sequence, which might be related to the poor restrictions on distance or on colors. They are weak objects. So another thing which we can examine is the projected orbital separations of our ultra-wide companion for our comparison samples A, B, and for example, SDB stars. As you can see, this cumulative probability does not coincide with any of our comparison samples. Instead, it goes somewhere between these two comparison samples. In reality, this simple comparison is not completely justified because some evolution happened, some mass loss happened, which did not occur in our comparison sample. So number of stars in comparison sample is larger. So to do this comparison more realistically, we performed simulations. So we took our values for separations in the comparison sample. And we assume that the inner star is not really a star, but a binary, which will go through a common envelope evolution and lose mass with the mass loss rate, with a different mass loss rate, ranging from 10 to the minus 6 solar masses per year to 10 to the minus 3 solar masses per year. And we see what only fastest mass loss time scale give us a result which more or less coincide with observations. Observations are here shown with a red curve. There is a significant difference between our simulations and observations around 2,000, 3,000 astronomical units. Which is probably related with limited resolution which we have in Gaia, because our comparison sample is located exactly at the same distances as SDB sample. It means we cannot really resolve orbital separations less than 1,000 or 500 astronomical units using Gaia. But during the common envelope evolution, part of the mass is lost and binary get wider. So there is additional increase in number of systems at 2,000 astronomical units. To match it better with our observations, we perform alternative simulations. So we look at a sample of main sequence stars located closer towards the sun, where we can resolve orbital separations around 500 astronomical units. And again, we assume that the inner star is actually a binary which loses mass on different timescales. So in this case, only simulations with mass loss rate 10 to the minus 2 solar masses per year satisfy our observations. So here my conclusion. We found 68 ultrawide companions to SDBs and 14 ultrawide companions to cataclysmic variables. Catalogs are available in this article, so you can perform modeling yourself if you want. A fraction of ultrawide companions to SDBs is 1.4%, to cataclysmic variables is something like 2.5%. And this is 2-3 times smaller than a fraction of ultrawide companions to main sequence stars and non-common envelope wide dwarf main sequence stars. So we assume what this difference appears as a result of mass loss during the common envelope stage. And if this assumption is correct, then we can put a lower limit on mass loss rate at around 10 to the minus 2 for SDB stars and 10 to the minus 4 for wide dwarf main sequence stars. So yeah, thank you very much for your attention.
Very nice. So, you have any questions? Sylvia, thank you.
Hey, Andre. Thanks for the nice talk and really cool, right? That triples are not only interesting objects, but they can be interesting tools as well. I have a question related to the statement that you had from Andre Tocqueville about ultra compact companions around different systems. So the thing I'm wondering is, if we look at binaries, so double main sequence, wide dwarf main sequence, and double wide dwarfs that are in these very wide orbits, then there's something very funky happening with the double wide dwarfs. So we don't see, we see far fewer double wide dwarfs in very wide orbits than we would expect. So I'm just a little bit wondering how that's going to play through in the triples here, because You know, if you see a similar effect in the triples, something is happening with these double white dwarfs. We don't see the widest orbits. If that same thing is happening in the triples, you know, then we, you know.
Yeah, I don't really know. So you mean what if you have just ultra-wide system with 2 white dwarfs? Okay, yeah. So in our case, this outer companion is mostly main sequence star, and we hope that it did not evolve enough to form a white dwarf. But yeah, it definitely requires further investigations.
That's a good.
I didn't know about this effect.
Yeah, but it's a good point that you focus on main sequence tertiaries.
Okay.
So actually working on this, it made me really wonder about the difference between, as you mentioned, the white dwarf versus the SDBs. Effectively, it's related probably to the mass of these components of the common envelope. And we found this difference. We found that in one case, the white dwarf, we get this lower and basically larger time scale, about 10 to the 4 years for the mass ejection compared to 100 years or less for the other ones. And so I just put it up as a question to the audience in general. I was wondering whether this could be related, for example, to ideas about recombination that might work better for low mass stars, but works less for more massive stars.
So your typical white dwarf progenitor is a 2 solar mass star. Your typical STB progenitor, Alexa, I'm guessing it's like 1.5 solar mass.
Yes. Although, I mean, perhaps a good thing to do is to try to distinguish between helium white dwarfs and carbon oxygen white dwarfs, because those have a bit different formation.
So it was more of a question, right? Not
I guess,
question,
I mean,
like a comment.
But Andrei, can you distinguish between what type of white dwarf they have in the white dwarf binaries?
Using Gaia, you mean?
Yeah. Can you put any constraints on the white dwarf mass?
I don't think so, but so how do you classify white dwarfs? Because I just don't know much about white dwarfs. Can you use colors?
Put very simply, if white dwarf had mass lower than 0.3 solar masses, it could be more or less confidently called a helium white dwarf, and it would be formed from a red giant. If white dwarf were massive than 0.5 solar masses, it probably would be a carbon oxygen white dwarf formed from an AGB star. And then the common envelope evolution leading to their formation could be different.
Sure, but can you distinguish these 2 white dwarfs using Hertzsprung-Russell diagram, or you need spectroscopy?
That would be better to ask an observer.
So you can, if you trust the distance Gaia will give you and you put it in an HR diagram, you can put it on a cooling curve, and that gives you an idea of the mass of the white dwarf. And of course, spectroscopy will do a better job, but then you need follow-up. But I'm very sure that all the not all, but that there's large efforts going on in following up the white dwarfs from Gaia with several surveys. So I'm sure that that will be coming.
Any more questions for Andrei? No? And I think since we're getting very close to what was advertised as the end of the session, I suggest we move whatever discussions there are left to Slack, either now or when you've had a rest, and meet back here tomorrow. And I want to thank all the speakers again, because, well, all of those I saw and the one I didn't see, which I watched on YouTube, I enjoyed. Yeah, thank you, everybody, and I'll see you tomorrow.
Thank you.